we come to the concluding part of our discussion on overview of experimental stress analysis, and this slide was shown at the beginning of this chapter. Now, you must be a lot more familiar on identifying various techniques that are depicted in this slide. Here you see the use of photoelasticity for finding out the stress patterns, and here you find the use of techniques like moire, holography or shearography to reveal various fringe patterns, and you find here this as the out of plane displacements. Now, you know that this is the slope, this is the curvature information, and each of this requires separate optical arrangements, and you may be able to get this displacements by the technique of holography or speckle interferometry or shadow moire. What you see is the simulated fringe patterns, and when you really make an experiment, the fringe patterns will follow this closely, but the quality of the fringes depend on what is the technique that is being used. And the moment you come here, you see this as butterfly fringes, and this you get from shearography. You can also get it from a variation of moire, and similarly you get this curvature fringes, and curvature fringes what we saw that you could get it from shearing interferometry, or you could also get it from some variation of moire technique. So, what you find here is now you have a familiarity how the whole field information looks like. So, this knowledge will go a long way in appreciating when you do the experiments what you have the patterns and how you have to interpret them and so on and so forth. And these two corner slides bring out the physics for each of the techniques. There is a physics behind it, and you have seen this is a method of caustics, and this is what you have seen in the case of moire, and you have beautiful moire patterns come, and the term moire has a origin from French. You have watered silk that was named as moire, and the same phenomena is when is seen in two gratings, it is also given the same name. And we have been discussing on selection of an appropriate experimental technique, and what we will do is we will go back and then review what we have seen till now. One of the crucial steps in experimental analysis is to identify a suitable technique for a given problem on hand, and we have seen that it depends on several factors: time available for analysis, level of accuracy required, range of strain or stress to be measured, influence of extreme conditions like high temperature, high strain rate, etc. Then you also have to look at what is the thoroughness of the study required, and finally, the cost permissible for the study, that is also equally important. Then what we looked at was, if the location of the point of interest in a component is known a priori, and if only a few in number, then strain gauge technique is the right choice, as it can be applied to various situations. And one of the greatest advantage of strain gauge is ideal for in situ measurements, that is becoming necessary for monitoring structural health, which is called structural health monitoring, and you need to do that for bridges, you need to do for dams, and several such structures are monitored over a period of time, and this comes as an ideal technique for that. You can also study for remote locations, you can also do it for rotating components, and can also work from elastic to plastic range, and also dynamic or transient phenomena. So, what we find here is it is more of a general purpose technique, and this is very advantageous when you go in for strain, if you want to get some information, then you can always fall back on strain gauges in some way or the other. Then what we have looked at first? We have also looked at in detail certain issues about using photoelasticity. Suppose I want whole field appreciation of the stress field, then photoelasticity is the right choice. We have seen for a stress concentration problem, plate with a hole, plate with a elliptical hole, and then you also saw a crack problem, and you also saw the spanner different designs. So, when I want to know what happens on the entire field, photoelasticity, you will be able to do it quickly. And as again, this also can be applied from static to dynamic analysis, and you have many variants of photoelasticity. They can be selected for measuring residual stresses, they can also be used for assembly stresses, and most importantly stresses interior to the body. Anything interior, whether you want to do it on human body, if you want to do a heart surgery, it is much more complicated than what you can do on the surface. It is very expensive, it is also delicate. Similarly, when I want to go and look at what is interior to the body, the problems are always complex, and photoelasticity provides the avenue. And you might have seen recently in the papers that Honda has asked certain components to be called back in the recent cars that they have fabricated, they have released to the market. So, when you are really looking at the design, you have such flaws and people have to call back and then replace the component, and in such applications a detailed analysis involving both numerical and experimental analysis is a must. And if you go back in history, many engineering applications people have done detailed 3-dimensional analysis using photoelasticity. So, this is one of its strong points as far as photoelasticity is concerned. And what you have is an intelligent use of photoelasticity with strain gauge can solve a variety of problems that commonly occur in normal design scenarios. Not only normal design scenarios, also in special situation. In fact, you have Concorde aircraft, though it is grounded now after the accident in France. This was one of the aircraft which had very least amount of failures in the field. There were no accidents till it was grounded, and it had a tail rudder which was failing repeatedly. In those days, about 70s, they are also done a finite element analysis to find out the cause for the rudder failure. From finite element point of view, the rudder is found to be reasonably strong to withstand the service loads, but nevertheless it was failing. Then what they did, they took a strain gauge and put it on the rudder and made measurements. When they compared that strain gauge values with design calculations, it also showed it is within the permissible limits. Then what they did was, but the component was failing in the field. So, you have to find out the cause. So, something what they could not identify from a numerical technique or a point by point experimental technique forced them to go for a whole field experimental measurement. So, they applied a photoelastic coating, then they found the maximum stress point was slightly shifted and strain gauge was reading only 2/3 of its maximum value. So, the moment they applied photoelastic coating, identified the point of stress concentration, then they put strain gauges, then that design was perfected and the problem was solved. So, what you need to do is, in many instances in practical problems, identifying what to do, which is the critical area itself is a challenge. So, a combination of whole field and a point by point technique, they go together and they help you to solve a problem. So, day to day design problem you can handle and also in special situations. So, you can always fall back on either photoelasticity or strain gauges. For special situation, what you have to do? You have to go in for special techniques. So, you need special techniques to address special problem situations. And the moment you think of Moiré interferometry, you have to think of electronic packaging industry, and you find it has found wide acceptance in electronic packaging industry to measure thermally induced stresses on tiny components. In this application, Moiré is ideally suitable, mainly because the components are very small. I can't go and paste a strain gauge, and Moiré gives a whole field information, and researchers have convincingly shown that Moiré is applicable for these class of problems. And we have seen for MEMS application, speckle and holographic methods are ideally found to be suitable. We have seen MEMS sensor, how speckle method could be employed, and we also saw in one of the references they have used holographic method to study a micro gear rotating at 3,60,000 RPM. So, MEMS application, if you have the need, then you think of either speckle or holographic methods. Then what you have? You have the method of thermoelastic stress analysis, and this is useful to measure stresses developed due to fatigue or random loadings, and that is a very special application people have applied using thermoelastic stress analysis. The methodology seems to be promising for unconventional applications such as stresses induced in slamming of automobile doors. See, you may think is it a problem worth analysis? In fact, more and more competition on automobile industry, people are very particular about the shape. So, they keep changing the shape of the automobile, and they are all having streamlined contours. They also travel at very high speeds, and there is also a pressure on them to bring out new variants, and this is all sheet metal work, and you need to find out for the given life whether the doors will withstand. So, slamming of the door is a random loading, and people found, because it is a 3-dimensional problem, it is not a 2-dimensional problem, because you have a contoured shape, and when you slam it and you need to make the measurement, and people found that you can apply thermoelastic stress analysis. It is very interesting. So, as technology advances, you also get newer and newer problems. In fact, if you compare the olden days, the cars did not have smooth contour, they were having box type and things. I am talking of 70 to 80 years back. Now, what you have, they all have streamlined contours, new manufacturing technologies, and more increase in speed. So, all that brings in new class of problems, which also require newer techniques to solve. The moment you think of vibration, holography is a ideal choice. See, I do not know whether you have done some experiments in your laboratory. When you want to find out the mode shape, you would normally sprinkle sand or lycopodium powder on a flat object. As long as I am working with a flat plate of different shapes, I can do the analysis with sand or lycopodium powder, find out the nodes. Suppose I want to do it for a turbine blade, which has a complex aerofoil shape, and it is also twisted. So, that is where holography came to the rescue, because it is essentially a out of plane measurement technique. It found interesting application on finding out the mode shapes of a vibrating component. And more composites and honeycomb panels are used in space technology. So, they all have the delamination problem, and speckle methods in its variation as shearography is very useful as an NDT tool in aerospace industries. And I have already cautioned that if you see butterfly fringes, you should not be happy, you should be rather sad that you have so much of delaminations and you need to go and repair it, then inspect, then only send. So, you have to be very careful about that. And what you need to look at is, I have been saying photoelasticity and strain gauges are general purpose tools. On similar lines, methodology of digital image correlation is also attractive as a general purpose tool. The technique is still developing and its accuracy level needs to be improved further for low strain measurements. Some time back the low strain was about 160 micro strain. Now people say even you can go up to 50 micro strain. So, as the technology is improving, you are also improving the capability of the technique to measure smaller values of strain, and this has a great potential. So, if time permits, we would also have some discussion on image correlation as we go by. Then what you have to keep in mind that whatever the guidelines that we have discussed so far, they are not complete, and the experimentalist acumen in deciding an appropriate technique is very much essential, and you will also have to use a intelligent use of an existing technique to unconventional situations is always welcome. You should never forget that, because seemingly complex problems you could attack it intelligently with simpler combination of existing methods. So, your engineering acumen is required. Like doctors have the acumen in detecting what is the disease, people go to only to that doctor when he is able to identify the disease correctly and then solve your problem. So, similarly engineers also have to understand what is the requirement of the given design scenario, select an appropriate technique and solve the problem. It is not that you are given a problem and you say that you will not be in a position to solve. Designers want some answer which they can use. They can always use a factor of safety if there is fuzziness in the answer, but some answer is always required. And another issue is, what is the level of accuracy that you can expect in experiments, and you have to understand there is no upper limit for accuracy. You can keep improving the accuracy in an experimental technique. You may start with a simpler rig and you make some measurements, and once you understand this scenario, you may want to improve it as much as possible. So, as one improves the experimental setup, the accuracy can be improved. So, there is no upper limit for accuracy, and you can keep improving the accuracy of an experimental technique. And what decides? It is a cost and time. The deciding factors are the cost and time available for analysis. So, if somebody designer wants a quick answer, you could give a number with certain level of accuracy, and he can always use a factor of safety and carry on with the design. And if he wants a very precise analysis, see normally when people design, if they want to make a helicopter to fly, they will make it fly first, optimization comes later. So, only when they go for optimization you need refined analysis. And when you are talking about accuracy, I would also like to caution, when you compare your experimental results with analytical solution. For example, if I want to find out the free end displacement of a cantilever, so you have PLQ by 3EI, and what you will do is you will find out what is the displacement from your experiment, and for the moment you consider that there is no shear deformation, the depth is very small. But even then, when I make my analytical calculations, I need to feed in the value of moment of inertia, and moment of inertia is b dq by 12. And if you do not measure the depth of the beam correctly, then what will happen? You will make an error on analytical calculation of the displacement, because I have b dq by 12, it will have a very high error, and PLQ by 3EI will not match with the experiment. So, you should not always blame the experimental technique when analytical and experimental techniques do not match. In your analytical calculation, have you provided correct numbers for you to do the calculation? That is also very important. People ignore. See, if I give a thin specimen to a student, he uses a scale and measure the thickness. You have to use a vernier and then measure the thickness. When thickness has to be measured, small distances have to be measured, you should use the precision, and this many people ignore. When they compare analytical method results to experiment, even for analytical calculation, you need to feed in some measurement by making actual measurements on the component or the object. So, these measurements also to be precise, and you should use method principle of statistics, take few measurements, take an average, all that you should employ. People never use statistics, they go and measure once and then say that this is the value. You will also always have to have an averaging procedure. So, that is also equally important. So, when we say experiments there is no upper limit for accuracy, you should also caution when you are doing an analytical calculation, those calculations have to be accurate enough. And what we will look at now is, based on the stress strain history, we will look at a broad classification of suitability of different techniques for different ranges of strain in the next slide. So, this is what we are going to look at. So, you can broadly classify based on the stress strain range you want to find out. And I have taken a typical stress strain graph. The idea is to show that I have a very small elastic region and a very large plastic region. The idea is to show that, and what we will look at is, you make a sketch of this stress strain curve, a typical curve, and we will go one after another: brittle coating, photoelasticity, strain gauge, thermoelastic stress analysis. In which range can you use it? Because a visual representation always helps to quickly identify, am I working on elastic or plastic region. And what way we looked at in brittle coating? Brittle coating, we all said that the failure strain of the coating decides the lower limit, and we saw that it is about 300 to 500 microstrain. As newer materials are developed, you may be able to bring it down, but the threshold limit is about 300 to 500. So, you will have brittle coating in this zone. So, you are operating in this zone. So, you have to start from this portion to this portion. This shape of the shadow is just for convenience, shape of the color is just for convenience. So, it is about 300 microstrain will be like this, because we always know that when it has this elastic point, it is about 2000 microstrain. So, we talk much below that, and we cannot go to lower strain levels in brittle coating, and this has been used to identify plastic deformation. So, this is the typical range where brittle coating can be employed. What you need to worry about this is the end point and the start point, roughly this range. And when I say photoelasticity, what does it indicate? I am essentially living in the elastic region. So, a photoelastic analysis will confine only in the elastic region, it will give you information. If I have to go for plastic region, I have to go for photoplasticity. Currently, we are only looking at photoelasticity. So, you will get this information for the elastic region, and the moment you come to strain gauge, We have seen currently you have techniques which can measure even 0.5 microstrain. So, that means almost close to 0, and you can also go to the plastic region about 10-12% of strain you can easily measure with strain gauges. So, you can also understand why we say strain gauge is a versatile technique. So, it has a longer range. I can go from elastic to plastic comfortably, and thermoelastic stress analysis is proposed as a whole field strain gauge technique. That is how they are propagating the technique now, and you can go from elastic to plastic region, and this is more of a whole field representation, but the instrumentation is very expensive, understand that. Strain gauge instrumentation is lot more simpler when you compare it to TSA, but even that instrumentation is costly, it is not cheap. And now you have a relative zones for different techniques shown. So, this is TSA, this is strain gauge, this is brittle coating, and this is photoelasticity. So, when you are confronted with a problem where you need to find out strain in a particular region, this graph you will be able to find out which way you will select the existing technique. Okay. I have shown only 4 techniques here. We will have a similar graph for other 4 techniques. They are grid methods, geometric moire, moire interferometry, digital image correlation, and you know grid methods were the one which is used for very high plastic region. Then you have geometric moire, and moire interferometry is refinement of geometric moire, and digital image correlation. It has a large range, but it does not have accuracy at lower strain levels. So, when you look at grid methods, the range is somewhere here. It is only in the highly plastic region you have the grid methods are applicable. And when you come to geometric moire, I would have it somewhere here. This is how I will be able to do this, and if I want to lower this, then I can go for Moire interferometry. And what you need to worry about is this end point and start point. This shape is for convenience, for aesthetic beauty some shape is drawn. The issue here is what is the range of strain that you are really looking at. And Moire interferometry cannot measure very small strains, it can go down, but it cannot go close to 0. And these are pictorial representation, no numbers are not given. So, you find that this is the range that you are really working with Moire interferometry. And when I come to digital image correlation, I can go from this to this, and I have already said that this can be brought down by improvement in technology. Researchers are working across the world, and they bring down this to as close to 0 as possible. They have now come to, their claim is now about 50 microstrain, and it is only a question of time that they improve the technique further, and now you have relative appreciation of various techniques. I have grid methods, I have digital image correlation, I have geometric moire, and I have Moire interferometry. So, this gives you a reasonable appreciation on how to decide the techniques based on the strain range. And now we come to the important step of looking at what are all the references that you need to have a look at. And you have a recently published Springer Handbook of Experimental Solid Mechanics. This has a large number of techniques compiled in one volume, and this is the third edition of such handbooks from Society for Experimental Mechanics, and this is edited by W.N. Sharpe. In fact, I have a chapter on photoelasticity in this handbook that covers the modern development of photoelasticity and also gives in a nutshell variants of photoelasticity. And this is a very useful reference. Then you have a very famous book, Optical Methods of Engineering Analysis by Gary Cloud, published in 1998. So, in all this you need the author, you need the year and the publisher. It is a university press, you will be able to access it. And what you also have to look at is Gary Cloud has given a series of articles in experimental techniques. He is writing articles on various optical methods for displacement, stress and strain measurement. Those articles are very, very interesting. You can have a look at it. It is in experimental techniques. Then you have a book on digital photoelasticity written by me, and this completely covers the development of photoelasticity from conventional techniques to digital photoelasticity, and exhaustively gives you various methodologies including phase shifting techniques and Fourier transform techniques, color image processing methods, and also application to fracture mechanics and stress separation, etc. Then you have a handbook of Moiré fringe technique. So, what I want to focus in this set of references is, for each of the technique you have so many books, and imagine if there could be a handbook specifically written for Moiré technique, imagine how many different types of optical arrangement they would have discussed. And in a small one semester course like this, we would not be able to do justice on all this. At least you should have these references and then have a look at it at your leisure time, or if you want to have additional information, you can always look at it. So, I have a handbook on Moiré published in 1993, and in 1994 high sensitivity Moiré, and here the focus is more on applying this Moiré technique for thermal stress gradient problems. You have this electronic packaging, what they have applied. Some of these also come in this handbook, but there is also a separate chapter that was written in the book on experimental analysis for mechanics and materials. Nevertheless, in this course we have had a look at basic physics, and that is the best that you could do in a course like this. And next you have two references on holography. I have a book on holographic interferometry by Rastogi. This is edited book in published in 1994. Then you have engineering applications of lasers and holography by Koch, published in 1979. And for each of the techniques, sub techniques also you have separate books available. And you have another book on holographic interferometry, CM West. And finally, you have a book on speckle metrology, a group of interferometric techniques. You have holography followed by speckle, and you have a book by R. S. Shirohi. He had a very good lab at IIT Madras, and several of his students have made significant contributions in the area of speckle metrology, and we need to be proud of. And finally, you have a book by Asundi. More and more computer processing is done, and he had come out with how MATLAB can be used for photomechanics. We have already seen when we looked at trends in experimental mechanics that the current trend is on finding out phase shifting techniques. They are used in several interferometric methods, and all these interferometric methods use CCD camera as an electronic eye, and image processing is done, and for many of these image processing application MATLAB could be advantageously used. That is why Azundi has come up with a book on MATLAB for photomechanics, and this is also an interesting book. And apart from this, I have been saying that you have for this course, you can follow the book of mine, and that is what we had seen earlier, that is what I am going to use for this course. And the CD looks like this, you have an ISBN number here, and even this conveys a message. The message what you have here is, you have conventional techniques like brittle coating, and this is your Moire for finding out in plane displacement, then you have strain gauges, photoelasticity. So, all the conventional methods which are time tested come in this category, and in this you find you have use of Moire interferometry for finding out crack tip stress field equations, and I have been saying that you have to use phase shifting methods, and this is the spanner where you find these are not fringe pattern, these are phase maps. There is a subtle difference between fringe pattern and the phase map, and this indicates the advancement of phase shifting techniques in the field. And here you have this laser speckle, and these are the white light speckle, and this is where image correlation is being used, and this is becoming a more of a general purpose technique. And this is the book which I will use, and in fact the book has more animations than what I show in this course. Then what we will look at is, I have an interest to look at your review of solid mechanics. This was given as your first assignment, and my interest is to bring out one or two important aspects from this assignment. And the first question is like this: in a 2-dimensional problem, without resorting to the Mohr circle approach, how would you find the principal stress and their corresponding directions uniquely? See, what you need to understand is, you have done a course in strength of materials where you find out principal stress direction, where you also find out principal stress magnitude. And if you look at in your learning, your focus was mainly on failure analysis. You were finding out Tresca yield criteria or von Mises yield criteria, wherein you need only magnitudes of principal stresses. You never bothered about the direction theta, and because you do not bother about direction theta, you also do not look at what are the nuances in finding out the direction. In fact, if somebody says you have an expression for theta, whether it represents maximum principal stress direction or minimum principal stress direction, you cannot half-hand say with your simple calculation of the trigonometric equation. Let us look at that equation. You will not be able to say that from that equation, and this is what the equation you have all learnt: theta equal to tan inverse 2 tau xy divided by sigma x minus sigma y multiplied by 1 by half. This expression being a trigonometric expression, it is multi-valued. So, it will give you multiple values of theta, and how will you associate it? You will be able to associate it if I go to Mohr circle. If you know how Mohr circle is drawn and how to interpret it, you will be able to fix up the theta what I have calculated corresponds to sigma 1 direction, the theta what I have calculated plus 90 degrees will give me sigma 2 direction, and normal calculation you do not require at all. So, you do not worry about it, and when I use this standard analytical expression, this expression cannot give it. So, you need to do something extra. So, when I do an experimental technique, you should also anticipate that if I have to find out the sigma 1 direction and sigma 2 direction, I need to find out, use auxiliary methods to convincingly find out whether it is direction for sigma 1 or sigma 2, and this was the problem in digital photoelasticity. So, the question is, how will you find out mathematically? So, you have to pose the problem differently. So, what you need to do is you need to pose the problem differently. You can do it as a eigenvalue eigenvector approach. Go to the fundamental definition of principal stresses. So, I get principal stresses as eigenvalues and the direction cosine nx and ny as the corresponding direction. So, I have the eigenvalue and eigenvector. So, when I repose the problem as eigenvalue and eigenvector, it is possible for me to find out the value of sigma 1 and corresponding theta, which you are not associated. You will know sigma 1, sigma 2. Many people also do not know how do we label sigma 1 and sigma 2. They are algebraically numbered. The greatest one is sigma 1, the smallest one is sigma 2 and sigma 3. That is how it is arranged. Any number you get is not sigma 1, you do not arbitrarily name it, there is a convention behind it. Now, the question is, I get two values of theta from this. Suppose I take the two least values, the first two values, how will I associate theta to sigma 1 direction and theta to sigma 2 direction? That I can do if I reformulate the problem as an eigenvalue and eigenvector approach. So, when I do that, it is possible for me to find out nx and ny from simple arithmetic, and you need to know that this has to be posed as eigenvalue eigenvector approach. That is good enough for you to go into the details of it. So, analytically also we need to do special efforts to find out this. So, when I do by experiment, particularly by photoelasticity, you will see that I have to use some kind of a calibration for me to associate the direction obtained to sigma 1 or sigma 2. And the emphasis here is more on finding out the principal stress direction here. And what we will now look at is the other question. You have the next question is stress tensor, find out the stress tensor in a transformed coordinate system. In fact, the whole of strain gauge analysis, if you know the tensor transformation law, you can comfortably understand. Stress is a tensor of rank 2, strain is also a tensor of rank 2. So, the second question essentially asks you to recapitulate your expressions understanding on transformation laws. So, once you know the transformation law, whole of strain gauges you can handle. And the third question is very interesting. What is the mathematical definition of a free surface? Specify the stress tensor on free outward corners, justify your answer. See, all this you have studied in solid mechanics, but you have not studied it with this viewpoint in mind. Okay. Now, let us get into the details of this now. So, what I have here is I have a mathematical definition of a free surface, and we have to go back and find out how do you get the stress vector. And what we have learned in solid mechanics, we have learned state of stress at a point. State of stress at a point gives you totality of all the stress vectors on all the possible infinite planes passing through the point of interest. So, you have if I take the point of interest, I have infinite planes passing through the point of interest. And how do you define a surface? A surface is defined by a outward normal. So, if n is the outward normal of a surface, then the stress vector on that plane is obtained as, you have all studied it. Can I have an answer from the class?
Stress vector can be obtained by multiplying stress tensor with the direction cosines.
What you have here is, I have Tn equal to tau into n, where this is the direction cosine vector and this is the stress tensor at the point of interest, and this is the stress vector acting on plane n. Plane is defined by outward normal and you have this as Tn. And what is the definition before we prove it? On a free surface, stress tensor need not be 0, but stress vector is necessarily 0. So, the mathematical definition of a free surface is Tn equal to 0. We will see this by an example. So, what we see here is, If I have to find out on any specified plane the stress vector, I can go to Cauchy's formula. Then I make a statement on a free surface stress vector is necessarily 0. So, it is defined like this, and what is the corollary of this? The corollary is that the stress vector direction on a free surface can at best be tangential to the surface. In fact, you have used some of these properties earlier in your course, but you have not looked at from this perspective, and this knowledge will go a long way in writing boundary conditions, not only in experimental stress analysis, but also when you apply numerical techniques. And this concept is not emphasized in your solid mechanics course usually. When experimentalists teach it, they may show that this is useful in experiments. So, this has to be emphasized, so that concept is developed. So, what we are now saying is a corollary of this is that the stress vector direction on a free surface can at best be tangential to the surface. In other words, stress vector cannot cross the free boundary. So, that is what I get from looking at Cauchy's formula and this mathematical expression, and finally, I come to the axiom that stress vector cannot cross the free boundary. You must have heard shear cannot cross the free boundary when you have done bending. The same thing is put in different words. It is more of a generic statement now. Let us take a simple example problem. I have a simple tension specimen, and let us consider a point B. Where is the point B? I have a point B located somewhere here on this, and I want you to tell now how will you classify this surface, the line which I am showing here. How do you classify this surface? That is a free surface, because it is an unloaded boundary, you can easily call it as a free surface. Now, what we are going to look at is, we will go and find out what is the stress vector on this surface. If it turns out to be 0, then what we have said, a mathematical definition of free surface is the stress vector on that surface is 0. We will indirectly prove that. And what we will do, we will take the stress tensor at the point, and that is given as like this, because I have what I have is I have the y direction, I have the y direction on this. So, I have some value, if I know what is the cross section, I can find out the stresses, and it turns out to be some magnitude A. So, stress tensor for this problem is given in this fashion. So, I know the stress tensor, and I have said that this is the free surface, and a surface is represented by its outward normal. So, let me find out the outward normal. I have n1, and how do you define the outward normal? You can easily write, it is nothing but 1 0 0, and you have a Cauchy's formula now. I have a stress tensor which is not 0, it has an element, but when I have this tau into n, what do I get? When I want to find out tau into n, I get this a null vector. So, you can go back and verify for several problems what you have studied in your strength of materials. Whichever problem you have looked at, you will invariably find that T n equal to 0 is completely satisfied on the free surface. Okay. I have also said there is a corollary. What is the corollary here? Now, I have this surface. Suppose I take a plane which is perpendicular to this, and what is the direction of stress on that? That is tangential. Okay. So, that is what it says. On a free surface, stress vector can only be tangential. The same thing, suppose I take a beam, this is free surface, this is free surface. So, on the free surface what I have? I can go back and calculate what is T n, and T n will be 0. suppose I cut it perpendicular, I will have stresses perpendicular to that. So, it will be tangential to the boundary. And the other one, suppose I have this as a cantilever beam and apply a end load, I consider this as the fixed end and I apply a end load like this, it becomes like a cantilever, then I will also have shear. And in shear what you have this as parabolic variation. When you have parabolic variation, you have top fiber is 0 and bottom fiber is 0. Why do you say that top and bottom fiber is 0? Because this is a free surface, shear cannot cross a free boundary, because shear exists in pairs. You have one shear, you have another shear here, because this is 0, this also has to be 0. A generalization of that is Tn equal to 0. Okay. And this is a very, very useful concept. The moment I know that shear cannot cross a free boundary, I know how the distribution of shear stress, I can picture it. It has to be 0 on the top fiber, it has to be 0 on the bottom fiber, because they are unloaded boundary. Okay. Now, what I have here, I have seen for this problem on a free surface stress vector is 0, we have seen. Suppose I take another problem where I have a projection, I have a projection like this, and I am not interested in finding out stresses at all these points. I would like to know what is the stress magnitudes at the sharp corner A. Can anybody say? When I have a sharp corner like this, suppose instead of this corner I have a corner which is like this, I have a cutout here, then it acts like a V notch and you have singularity at the crack tip, at the angle and so on, you call that as re-entrant corner. Suppose I have a outward corner, I can go from my knowledge of stress vectors and then show that this tip stress tensor has to be 0, a very useful information. And what I have here is a free outward corner represents intersection of two free surfaces, as in point A. I have this is a free surface given by outward normal N1 and this is a free surface given by outward normal N2, and what I have, the stress vector can only be tangential. So, if I take this point, it can be only tangential like this, or if I take this surface, it can be tangential only like this. So, I cannot have a contradiction. For the contradiction to satisfy, it would create an anomaly. So, I have to have stress tensor to be 0. So, it contradicts the definition of free surface, and finally, what you have is stress vector can be 0 only if stress tensor is also 0. It is a very useful information. In fact, when you go to photoelasticity, when you want to find out the fringe orders, this will be used as one of the methodologies to find out the 0th fringe order. And you can also verify when you have a finite element solution and plot it. If you have stresses on free outward corners, then you can go and tell the analyst you have done something drastically wrong on the boundary conditions. So, it is both useful for fringe ordering in photoelasticity, also for verifying your finite element solution, and this is a very useful result. So, what I have here is I have a sharp corner and this is the outward corner. I have seen this outward corner. What happens to this outward corner? The same logic holds good, and particularly in this case there is also another subtle point. I am applying a load with a pin, I am applying load only here. So, on the entire surface what happens? In this particular loading arrangement, the entire surface also has 0 stress, okay. But in general, any free outward corner like this, you will have stress magnitude, stress tensor is also 0, not only the stress vector, stress tensor is also 0, and that is a very useful concept that you can use. take advantage of. So, what I have here is I have a set of only 5 simple problems, and then the next problem is essentially you have to find out the shear distribution on a 3-point bend specimen. Suppose I have this as the beam and I have supported like this, and I put a sharp load like this. Now, what I need to do is, from your strength of materials, if I want to find out the shear distribution over the depth, what is the variation? It is a parabola, okay. But what will be the variation when I come closer to the loading point? It is no longer a parabola. In fact, if you go and look at the way you learnt shear force and bending moment diagram, you started with concentrated loads. You found out the bending moment diagram, shear force diagram. But if you go and look at theory of elasticity, you would have started with distributed loading, because at distributed loading I can specify the boundary condition easily. I will find it extremely difficult to specify the boundary condition when I have a concentrated load. I have to use Fourier harmonics and then take several harmonics and then only find out what is the load acting on the member. In principle, I can solve shear distribution by theory of elasticity for this problem also, but that would be very complicated, and you will find it is no longer parabolic. The shear is still 0 at the top fiber, because we have seen shear cannot cross the boundary, free boundary, and you will have a maximum value near the surface and reduces to 0. So, if you do not put reinforcement, your design will fail. So, that is the pulse of the third question, and this is interrelated to the earlier question, and you will go and find out in photoelasticity shear variation can be easily identified without much effort by a simple photoelastic analysis. So, that is part of your lab exercise. So, this brings to the conclusion of overview of experimental stress analysis. In fact, I have followed a different approach, wherein we had looked at what is the advantage of an analytical, numerical and experimental method, what are the differences, what are the specific features of each of this. Then we moved on to what an experimental technique give directly. So, that gives you an information that is linked to the physics of the experiment on which it is based. Then we looked at what these experiments, how the physics is employed, what is the physics behind each of these experimental technique in some detail. In the process, I have also said which class of problem this could be applied. Later on, we also saw how to name an experimental technique, what are the trends in experimental mechanics. Then we also had a reasonable discussion on selection of an appropriate experimental technique. In fact, that is very crucial. If you have that mindset, when we discuss some of the techniques in detail later, you will always look for, while understanding the development of the technique, which class of problem this could be applied. That thinking process also will get initiated, and that you see in a very unique way in the presentation which we had seen. We had also looked at, as a function of range of strain, how these techniques could be selected. And I am sure at this stage you are quite clear that each of the experimental technique exploits a particular physics, and if you understand the physics, then you can do interpretation. And we have also seen the literature on this is voluminous. In fact, doing justice to all the experimental techniques in a one semester course is extremely difficult. So, we would focus our attention on photoelasticity. We will essentially see transmission photoelasticity, reflection photoelasticity, and also some ideas about 3-dimensional photoelasticity. Then we will spend time on strain gauges and also a little bit about brittle coatings. If time permits, we will also spend a few lectures on digital image correlation, because it is an emerging technique. And with whatever we have discussed, if you are interested, you can always go to any one of the references and read, do self reading and try to find out how those techniques could be employed, ready made equipment available and so on and so forth. Thank you.